In this video, we are starting Chapter 15, so this is Chapter 15, Part 1. Chapter 15 is on oscillations, and this video is how simple harmonic motion can be represented mathematically, and this corresponds to Section 2 in your textbook. So periodic or harmonic motion is any motion that repeats itself at regular intervals, and simple harmonic motion is periodic motion that is a sinusoidal function of time. So simple harmonic motion is a special case of harmonic motion. Now what we want to do in this video is figure out how back and forth motion like this can be represented by a function. So let's gather some data that will hopefully help us see where we need to go. This is a picture of a pendulum, and at time 0, this pendulum is at position 0.5 meters. So let's record that data. The pendulum will swing so that at 1 second it'll be at 0 meters. It'll keep swinging. At 2 seconds, the pendulum will be at negative 0.5 meters. It'll then swing back so that at 3 seconds it's back at its equilibrium position, or 0 meters. And then at 4 seconds, it's back at 0.5 meters. So let's graph this data. We'll do that on the next slide. So you can see here that I've graphed the data, and if we trace this curve, we can see, and it would keep going, we can see that it makes a sine or a cosine curve. So we have a better idea. We know it'll be a cosine or a sine function. Here's some other data that was gathered about a particular pendulum. Let's get some vocabulary under our belts. So amplitude is the maximum displacement from equilibrium, and that'll be whatever is on the outside of the sine or cosine function. In this case, the amplitude is equal to 2. Another thing we need to know to get the position as a function of time is the period. The period is how long one cycle takes. So whenever the particle returns back to its original position, and in this case, the period is 3 seconds. So we have a starting point. We also may need to know the frequency, and that's defined as how many cycles per second. The units are hertz, and it's the inverse of the period. So in this case, the frequency is 0.33 hertz. So far we know that we'll have xt equals 2 cosine something 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 t. Again, we know that the 2 is on the outside because that's the amplitude. So what if we just graphed 2 cosine t? Well, you can clearly see that's not right, because the period that we had before was 3, and this graph is showing us a period of a little bit over 6. So we know we're going to need something before the t so that we can get the period to be equal to 3. So we need to figure out some kind of constant here. Let's go back to some of our data. We know that at position 0, the time is 0.75. And we're going to call that constant omega because that's the convention. It's something known as angular frequency. So we can just divide both sides by 2 and then take the inverse cosine of both sides. And then we can keep solving for omega, and we get that omega is equal to 2 pi over 3. So that's the constant that needs to go here. But how is omega related to period? When omega equals 2 pi over 3, the period is equal to 3. So the relationship between omega and the period is that omega is equal to 2 pi over t. So the equation that we have for our data is xt equals 2 cosine 2/3 pi t. Here are some important formulas. So this formula right here is just the general formula for position as a function of time of an object undergoing simple harmonic motion. On your formula, on your table of information, they call A x max. Another formula that's on your table of information is t equals 2 pi over omega, and then we also know that's the same as the inverse of the frequency. So omega is called the angular frequency, and it's just the oscillations per second divided by 2 pi. And then this right here, phi, is the phase constant, and it depends on the displacement of the particle at t equals 0. So it happens when the cosine function is shifted to the left or to the right. So here's an example. This was our original function, and then the red one that you see is when the cosine function is shifted, so negative pi over 4 is the phase constant. So it shifted to the right by 1/8 of a cycle. Now, since we know position as a function of time, we can pretty easily get velocity and acceleration by using a little bit of calculus. So to get velocity, we want to just differentiate the position function. So you need to use the chain rule, so you do the derivative of the inside and then multiply it by the derivative of the outside. So the velocity as a function of time is this. And then the acceleration as a function of time, you just differentiate the velocity function. And again, you have to use the chain rule. And you end up with this down here for the acceleration. So there's a lot of information in this video, but just keep in mind that the most important formulas are on your table of information.